So you're curious about quantum mechanics and its interpretations? Excellent choice. Quantum mechanics is like the rock star of physics, mysterious, fascinating, and just a bit mind-bending. Today I'm going to break down the major interpretations for you, and trust me, it's going to be a wild ride. First up, we have the Copenhagen interpretation. This one's the classic. It's what you'll find in most textbooks. The Copenhagen interpretation says that particles don't have definite states until they're observed. Picture Schrödinger's cat. Until you open the box, the cat is both alive and dead, but not everyone's sold on that idea. Enter the many worlds interpretation. This one's straight out of science fiction. It suggests that every possible outcome of a quantum event actually happens in its own separate universe. So in one universe, Schrödinger's cat is alive, and in another it's dead. Infinite universes, infinite possibilities. Next, let's talk about the de Broglie-Bohm theory, or pilot wave theory. This one's a bit old school, but super interesting. It says that particles have precise locations at all times and are guided by a pilot wave. Unlike the Copenhagen interpretation, it's fully deterministic, no randomness here. Every action has a specific cause and effect. Then there's the quantum Bayesianism, or QBism for short. This one's more philosophical. It treats the wave function as a subjective tool, representing an observer's knowledge rather than an objective reality. In other words, quantum mechanics is all about updating your personal beliefs based on new information. Lastly, let's not forget the collapse theories. These interpretations propose that wave functions collapse spontaneously without measurement. Think of it as nature's way of choosing one reality over another. It's like the universe gets tired of being in limbo and just makes a decision. So why haven't we settled on one interpretation? Good question. Each interpretation comes with its own set of puzzles, and none of them has been definitively proven or disproven. That's what makes quantum mechanics so exciting. It's still an open book with endless questions to explore. In the end, the interpretation you lean towards might depend on your philosophical inclinations. Are you a fan of determinism, or do you prefer a dash of randomness? Do you think reality is subjective or objective? These are the questions that keep physicists and philosophers up at night. Hold your seats tight, because we will dive very deep into each interpretation of quantum mechanics. Before that, we must understand the two essential qualities all the interpretations share. More or less, all interpretations of quantum mechanics share two qualities. They interpret a formalism, a set of equations and principles to generate predictions via input of initial conditions. They interpret a phenomenology, a set of observations, including those obtained by empirical research and those obtained informally, such as humans' experience of an unequivocal world. However, two qualities vary among interpretations: epistemology and ontology. Epistemology deals with claims about the possibility, scope, and means toward relevant knowledge of the world. Ontology, on the other hand, deals with claims about what things, such as categories and entities, exist in the world. In the philosophy of science, the distinction between knowledge and reality is termed epistemic versus ontic. For instance, a general law can be seen as a generalization of the regularity of outcomes, epistemic, whereas a causal mechanism may be thought of as determining or regulating outcomes, ontic. A phenomenon can be interpreted either as ontic or as epistemic. For instance, indeterminism may be attributed to limitations of human observation and perception, epistemic, or may be explained as intrinsic physical randomness, ontic. Confusing the epistemic with the ontic, if, for example, one were to presume that a general law actually governs outcomes and that the statement of a regularity has the role of a causal mechanism, is a category mistake. In a broad sense, scientific theory can be viewed as offering an approximately true description or explanation of the natural world, scientific realism, or as providing nothing more than an account of our knowledge of the natural world, anti-realism. A realist stance sees the epistemic as giving us a window onto the ontic, whereas an anti-realist stance sees the epistemic as providing only a logically consistent picture of the ontic. In the first half of the 20th century, a key anti-realist philosophy was logical positivism, which sought to exclude unobservable aspects of reality from scientific theory. Since the 1950s, anti-realism has adopted a more modest approach, often in the form of instrumentalism, permitting talk of unobservables but ultimately discarding the very question of realism and positing scientific theory as a tool to help us make predictions, not to attain a deep metaphysical understanding of the world. The instrumentalist view is typified by David's famous slogan, "Shut up and calculate," which is often misattributed to Richard Feynman. Let's dive into one of the most enduring interpretations of quantum mechanics, the Copenhagen interpretation. The Copenhagen interpretation is a collection of views about the meaning of quantum mechanics, principally attributed to Niels Bohr and Werner Heisenberg. It is one of the oldest attitudes towards quantum mechanics, as features of it date to the development of quantum mechanics during 1925-1927, and it remains one of the most commonly taught. However, there is no definitive historical statement of what constitutes the Copenhagen interpretation, and there were fundamental disagreements between Bohr and Heisenberg. For example, Heisenberg emphasized a sharp cut between the observer, or the instrument, and the system being observed. On the other hand, Bohr offered an interpretation that is independent of a subjective observer or measurement collapse, relying instead on an irreversible or effectively irreversible process that imparts the classical behavior of observation or measurement. Features common to Copenhagen-type interpretations include the idea that quantum mechanics is intrinsically indeterministic, with probabilities calculated using the Born rule and the principle of complementarity. This principle states that certain pairs of complementary properties cannot all be observed or measured simultaneously. Moreover, properties only result from the act of observing or measuring. The theory avoids assuming definite values from unperformed experiments. Copenhagen-type interpretations hold that quantum descriptions are objective, in that they are independent of physicists' mental arbitrariness. The statistical interpretation of wave functions, due to Max Born, differs sharply from Schrödinger's original intent. Schrödinger aimed for a theory with continuous time evolution where wave functions directly described physical reality. Now we delve into another fascinating interpretation of quantum mechanics, the many worlds interpretation. The many worlds interpretation posits that a universal wave function obeys the same deterministic reversible laws at all times. Unlike the Copenhagen interpretation, there is no indeterministic and irreversible wave function collapse associated with measurement. Instead, the phenomena associated with measurement are explained by a process known as decoherence. Decoherence occurs when quantum states interact with their environment, leading to a situation where parts of the wave function describing observers become increasingly entangled with parts of the wave function describing their experiments. This entanglement results in all possible outcomes of experiments continuing to exist within the wave function's support. However, these outcomes become correlated with observers at different times, effectively splitting the universe into mutually unobservable alternate histories. In other words, every possible outcome of a quantum event actually occurs, but in separate parallel universes that do not interact with each other. Next comes the transactional interpretation of quantum mechanics. The transactional interpretation, proposed by John G. Cramer, is inspired by the Wheeler-Feynman absorber theory. This interpretation provides a unique perspective on the collapse of the wave function. According to TIQM, wave function collapse results from a time-symmetric transaction between a possibility wave from the source to the receiver, known as the wave function, and a possibility wave from the receiver back to the source, known as the complex conjugate of the wave function. What makes this interpretation particularly fascinating is its view of the wave function as a real entity. In traditional interpretations, the wave function is often considered a mathematical tool rather than something physically real. However, TIQM takes it a step further by also treating the complex conjugate of the wave function, which appears in the Born rule for calculating the expected value for an observable, as equally real. This time-symmetric approach suggests that quantum events are not just influenced by past conditions, but also by future conditions, creating a more holistic and interconnected view of quantum phenomena. As we continue our journey through the fascinating interpretations of quantum mechanics, let's delve into the enigmatic von Neumann-Wigner interpretation. In his seminal work, The Mathematical Foundations of Quantum Mechanics, mathematician and physicist John von Neumann tackled the notorious measurement problem. He proposed that the entire physical universe could be governed by the Schrödinger equation, encapsulated as the universal wave function. According to von Neumann, measurement could trigger the collapse of this wave function. This intriguing perspective was further expanded by physicist Eugene Wigner, who suggested that the conscious awareness of a human experimenter or even a dog's consciousness might be crucial for the wave function's collapse. However, Wigner later distanced himself from this idea. Despite this, the role of consciousness in quantum mechanics remains a captivating mystery. The nature and origin of consciousness are still not well understood. While some have proposed that consciousness causes wave function collapse, these theories often remain unfalsifiable. This leaves us with many questions about the intersection of consciousness and quantum mechanics. Last but not least, we have the concept of time-symmetric quantum mechanics. This idea was first suggested by Walter Schottky in 1921 and has since evolved through various theories that modify the equations of quantum mechanics to be symmetric with respect to time reversal. These theories introduce the idea of retrocausality, where events in the future can affect those in the past, just as events in the past can influence the future. Unlike conventional interpretations, a single measurement cannot fully determine the state of a system. However, given two measurements performed at different times, it's possible to calculate the exact state of the system at all intermediate times. In this view, the collapse of the wave function isn't a physical change to the system, but rather a change in our knowledge of it due to the second measurement. This approach also offers a new perspective on entanglement. Instead of being a true physical state, entanglement is seen as an illusion created by ignoring retrocausality. The point where two particles appear to become entangled is simply where each particle is influenced by events occurring to the other particle in the future. Not all advocates of time-symmetric causality favor modifying the standard quantum mechanics. For instance, Lev Weidmann, a leading exponent of the two-state vector formalism, believes it aligns well with Hugh Everett's many worlds interpretation.